Ali, do you see that okay?
Yep.
Okay, cool. I'll get rid of this. Okay, and then we're also going to pull up the GoProgs repo. So the linear search algorithm, this is the naive part of working up to a binary search progression. So the instinctive or the knee-jerk way of searching through a list for an item you're looking for is just to go from the beginning of the list and just progress through it until you find the thing you're looking for. Uh-oh, what's going on with my internet? There we go. So we have this function here, and we're just going to fill in the details. So we're going to be provided a slice of sorted integers, and that's really important for the binary search, but not so much for the linear search. And then we have a needle, the thing that we're looking for. And what we're going to do is we're going to return the index of where that needle is in the haystack, or where it should be if we want to insert it. And
Got it.
yeah, I think that's it. These are invalid values that are being returned. -1, we should never have a negative index. It should always be either the index we want to insert it at, or either the index it exists at, or where we want to insert it. And we also have a corresponding test. I'll pull that up. So there's two main parts to this test. Let me blow this up a bit. So the first part is that we have a bunch of fixtures for the haystacks, the needles, and the expected indexes. And then we have another part of this is that we split up. We're reusing parts of the test for the other algorithms. In our case, we're doing a subtest for linear search. And then if we finish that, we'll get to a subtest for binary search. Okay. So I'm going to go to the project in my Go path. Okay, and then I'm going to go to algorithms, and we have binary search there. I'll blow this up a bit. So we're going to modify this file right here. Oh, and actually I was wrong here. So the way these tests are written is that if we can't find it, we're going to return a negative value. So I don't want to rewrite the test. So we'll stick with that rule for now.
Okay.
So Ali, do you have any, do you want to shout out the answer to this? How to search linearly through a list?
I would guess using the range thingy. I don't know what the terminology for that is, but
I think range
or
thingy
yeah,
is
I guess like a for loop using the range operator.
Yeah, I think range thingy is what I call it too. So when we're using range, we're going to get two values. One of those is going to be the index, so I'm going to call that I. And then the other thing that we're going to get is the actual value. So I'm just going to call that actual. I can't think of a better name. So we're going to be ranging over the haystack. And what we're going to do is we're going to compare the actual to the haystack. And just to make things more obvious, I'm going to print what's going on here. Actually, I'm just going to print I and actual so we can see that. And I'll print out what we want, the needle. So let's just do that. And I have to have a return value. So I'll keep that -1 there. And then I'm going to just open a separate terminal to run these tests. Let's do that. So I'm going to run the test with verbose turned on, and I'm going to run it focused on only the test that we want. So the test that we want is test search. And the subtest that we want is linear search. So I think the way that Go does this is that it puts like an underscore for spaces in the subtest name. I believe that's what it does. Okay, so we've got an issue here already. It doesn't like, oh, because, okay, this is why. It doesn't like that. So the reason why is I was using the wrong function. Printf is a formatted print where it expects a string that has like formatting directives inside of it. So this will allow us to just print random types. Okay, cool. So we got a failure here. And that's because we haven't really done anything yet, but we got a log message that printed all the different values here. So on the first iteration of this test, I is 0, actual is 1, and needle is 1. So it shows you that the I, it's always going to be 0 based. Indexing starts at 0. It's going to go up and higher. Now, there's only one item, or actually, there's no items in this. Yeah, so we actually passed the first test because we returned -1, and that's what they want here. The second test is where we failed. There's only one value in here, so we should have returned index 0. So to get this to pass, what we need to do is actually we need to check, if needle equals actual, we're gonna return I. So that means that we've found the thing that we're looking for. So let's see what happens now. Okay, now everything passes. That's it, we're done. Like, this is a pretty simple thing to do, just doing a linear search. I've probably written a million of them. Ali, what about you? Have you written a lot of linear searches?
Um, Probably, yeah.
I think that's the go-to in Go. Like, if you have a list of things that you're looking for, you just iterate over them. So we've got some discussion questions here. What is the big O time complexity and space complexity of this solution? Do we have anyone else on? Am I just picking on you, Ali, when I could be picking on someone else?
So time complexity is pretty straightforward given the name. It's linear because wait, is it?
Yeah.
Oh yeah, it's linear because the time increases linearly with the size of the list.
Yeah, in worst case, we're going to have, if we have n items in the list, the worst case is going to be big O n. So yeah, that's whenever you see something that is just big O n, that's key for linear. Space complexity. I don't think we used any extra variables here, except for a couple little variables here and there, which are it's just a constant number here, so we can ignore that really. So yeah, the space complexity is just big O1, I think. I don't think
Yeah, I think that makes sense.
yeah. Yeah, it doesn't, the space complexity doesn't increase as the number of elements increase. We're just reusing a couple variables here that we've declared to copy the values of the current element we're in. So that's pretty simple. So when is linear search appropriate? like I was saying earlier, I've written a lot of these, and it's because it's simple. It's really easy to write a linear search. You're just ranging over a list, and when you find what you want, you exit the list. So the big thing is when performance doesn't matter, linear search is really nice. And a lot of times, at least I think the work that we do here at GitLab, a lot of times the bottleneck is not how long it takes you to traverse over a simple list in memory. It's usually something else like disk or network or something to that effect. If you have a small list of things, then linear search is good enough a lot of times. Can you think of anything else? Another reason why we'd want to use linear search?
I think you explained it pretty well. I think it's also important to think about like what's the biggest, what's the largest list you could get, because if you know that it's guaranteed to be small, then linear search completely makes sense. But like if if there's like some edge cases, for example, where you might get a large list, like if you don't control it very well, like if it's out of your hands what you're getting, then you might want to consider the trade-off of complexity for like a little bit better performance in those cases.
Yeah, that's a good point. I think the big rule that people should follow is, add complexity after you've noticed or you anticipate a performance degradation. And using measuring tools is a good way to do that. Understanding the background of the problem when you're implementing a solution is important. Um, another time I think that linear search is appropriate is when the solution, when you know that the thing you're looking for tends to be at the beginning of the list. So if you've got some kind of data structure that is moving, like let's say you have like a stack or something, or some kind of priority queue, you have some type of data structure that moves the most commonly accessed data to one end, then if you start your search from that end, chances are you're going to get the data that you're looking for. So if you're in that kind of situation, linear search might be nice in even, like a large complexity set of data. There's also ways that you can enhance linear search. So one of the things that I found while researching this problem is that there's variations of linear search and binary search where if you don't find what you're looking for on the first one, you try to take a guess and like jump ahead in the list a certain amount. And then if you don't find it, maybe you jump more. And then once you do pass the value you're looking for, since this is a sorted list, then you can backtrack and you can do something like that. I think that might be used a lot. I don't know for sure as a fact, but I think that might be used a lot when you're dealing with like rotational disks and sequential memory, that sort of thing. If you're scanning through a large set and you want to find something, you might ramp up your linear search and speed
Yeah,
up because you know
that
that you
kind of
find it.
that kind of reminds me of an interesting data structure called a skipped list, which I don't remember exactly how it works, but it's basically like you have the entire list as one array, and then you also have another dimension where you have let's say every 10th item is in the second dimension of the list, and then as you go higher, you sort of make the items less frequent. So you can sort of scan through the top dimension of that list to figure out, like, probably not explaining it very well, but
You said that
yeah,
was
a diagram really helps to see.
oh, they got a little animation here. So it
I
just
mean, it's
knows.
it's not exactly linear search, but it is. You are
Mhm.
sort of progressing through it linearly. Like you go down in the dimension every time you find something close to what you want, type of thing.
That's cool. I'm going to link this in our docs, and we can follow up with this in the issue. Yeah, so some of this stuff I think, we're kind of analyzing it to death, but this is like really intuitive stuff for people. Like when you're naturally dealing with like a large set of data, you want to kind of skip ahead and like find these markers and insert things into a specific slot, right? Like that's kind of how we do things on a day-to-day basis. We kind of skip ahead and then we get our bearings and then we adjust. So yeah, this is cool. I'm going to read this.
Yes, it's like in real life, like if you're looking for a word in a dictionary, that's pretty much exactly the kind of thing you would do.
Yeah, you would
And
kind
I
of
guess,
flip past it and then you'd be like, oh, I went too
yeah,
far, and you go a few pages back.
yeah.
Cool. Okay, so we got a solution to linear search. Now, let's move on to the prize cow here, the binary search. So there's two ways we can attack this. We can go for an iterative solution, or we can go for a recursive solution. I think we should go for the iterative solution first, because that one, it makes everything obvious. And then once we make everything obvious, then we can kind of reduce it down to a more elegant solution recursively. So
Okay.
Just to recap on what binary search does, we have a big list of sorted items. We're going to be given an item that we're looking for, and we're going to keep slicing the problem set in half to find that solution. So first we're going to slice in half in the middle. We're going to see, is this middle element what we're looking for? And if it's not, we're going to go left or right to divide the problem into pieces. So we've done all the little language mechanics to train ourselves for how to deal with slices and how to access indexes and how to do recursion. So now we're ready to actually implement this and put it into use. So how should we start this? What's the first thing that we do when we start a binary search? Ollie, you got anything? Any suggestions? I'm going to say that I think we should check for abnormal edge cases so that we don't have to waste our time looking at weird things like, for example, if it's empty. So let me pull up the, let's see here, where's the actual test? So we have some weird cases like where we have an empty list. And if we're going to be accessing the middle element, we don't want to be doing that on an empty list because we're going to have an out of bounds panic. So the very first thing I'm going to do is say if the length of the haystack is less than 1, then just return -1. I think in all other cases, we do not want to return -1. Actually, no, actually, based on the rules that we have, we'll still return -1 if the item doesn't exist in the list. So we can still return -1 as a default case. So I'll leave that back in. Once we've checked that there's a value there, we need to know what the middle point is. So I'm going to call that mid. And mid is going to be the length of haystack divided by 2. So we have this needle. Oh, and actually, yeah, so we have this needle. We need to check, is that needle the middle point? If it is, we're done. So if needle equals haystack at the midpoint, then we can just return needle and we're done. Or sorry, not needle. We can return mid. and then we're done. So let's see here. What happens if I run that code? Searching for needle 1 and haystack 1, 3. So I'm looking right here. Got index -1, but wanted 0. So this fails. This fails if we have 2 items in the list. Oh, for some reason, why am I? It's running the meta beta binary. Oh, this string. So the way Go does tests is it just matches this string here with this string here, but I guess it doesn't matter if the slash is there because it still is running a meta binary search. That's funny. Didn't realize that. So we can just ignore this for right now. We're focused on just the binary search. So this test right now, it does not iterate over the entire list. There's no for loop there. It's just looking at the first element, and if the first element, it works, then it returns it, returns the solution. Otherwise, it just says, I don't know how to do anything else. Here you go, -1. So we need to take this, this solution right here, and we need to generalize it for every single element in the list. And we need a for loop to do that. So we're going to be iterating over everything. And I'm just going to put a forever loop here. So this loop will just run forever until I either return or break from the list. So the problem is we need to save our place throughout this loop. We need that to be, we need that information accessible from loop iteration to loop iteration so that we can progress. So what I'm going to do is instead of declaring the midpoint, or instead of declaring where we are in the list at the inside of the for loop, I'm going to do that outside the loop, if that makes sense. Actually, we don't define it at all right now. So what I mean is that there is a implicit set of arguments here that we're working on. We have the start and end of the loop. Right now, the start of the loop is haystack at 0, and then the other thing is the end of the thing, which is length of haystack -1. So the midpoint is relative to the start and end. But if we're dividing the problem smaller and smaller, we need to be able to adjust the start and end based on what it was previously, if that makes sense.
Mm-hmm.
So what I'm going to do is I'm going to move this over here, and then in here we're going to modify start and end based on where based on how the needle and the current element, the midpoint, compare. So another thing that I'm going to do here, we just check if it's equal, but if it's not equal, the best case is that it's equal and we're done. We found the solution. If it's not equal, then that means that we need to check if it's less than or equal to or greater than. So what we can do is we can, instead of having a if statement, we can have a switch statement because we have 3 cases really. We have the case that needle is equal to the haystack mid. And then in this case, we return mid. Then we have the case that needle is less than haystack mid. And so we're going to come back to this. And then we have the case that needle is greater than haystack mid. And we'll come back to that. So now we see that we need to define these points. And then another thing jumps out at me. We have this midpoint, and this midpoint right now, it's going to be the same thing over and over again, every loop of this, every iteration of this for loop. This midpoint will always be the length of the whole slice, and then we're going to divide that in two. So we want this midpoint to change relative to the start and end. So we need to modify that. Ollie, do you want to take any jabs at this? How do we update this midpoint so that it's always relative to the start and end that we've defined on line 21?
I think midpoint should be the difference between start and end divided by 2 instead of length of the haystack divided by 2.
Okay, so that's the difference between start and end divided by 2. So are there any edge cases here that we should be worried about? Can we end up with any kind of, like for example, can end minus start ever be 0 and cause this to, let's try this. Let's try running this.
I guess if there's one item, then start and end are the same thing.
If there's one item, because the start is 1 and the end is 1. So you end up with 0 divided by 2. So do we need to do a check before this line?
Yeah, I think we could add a one item list as one of our edge cases and do it like right below the place where we check if there are no items in the list.
So our second case in the test is actually one item on the list, so we'll get to see that. So the other thing is we're going to end up with a forever loop because we don't exit on these other cases here. We're just continuing to change. So what we need to do is we need to update start and end so that based on where we want to go left or right, we update the section of the slice that we're dealing with. So if needle is less than the midpoint, the thing that we're looking for is less than the middle point we've chosen, then that means we need to go left. So I'm going to put go left here. And then in this case, we are going to go right. So if we're going left, what does that mean that the new start and end are?
Start would remain the same, and end would get cut in half.
Okay.
End would be mid, just to make it simpler.
End would be, can you say that again?
End gets assigned to mid.
To mid.
Yeah, end is equal to mid, basically.
Okay. And then if we're going right?
If we're going right, then end remains the same, and mid becomes the start. Or start becomes
Yeah, and I just goofed right here by putting the combination assignment. We don't want to reassign. We want to use the same variables that we declared outside the for loop. So we don't want to shadow these, in other words. Okay, cool. The only thing missing here is some logging to get an idea of what's going on. So what I'm going to do in the for loop is I'm going to log, and I'm going to put a really cool emoji to, let's see here, let's choose, I like using emojis because they stand out in the logs if you have a lot of log messages. Let's pick the monkey.
That's actually a really good tip. Like in the past, I've just used like a bunch of hashtags or dashes or something, but yeah, an emoji really does stand out.
Yeah, the only problem is sometimes in a terminal, the emojis, they'll be variable width, and sometimes they'll cover, they'll obstruct a character that's right next to it. So I always put a space after the emoji so that if it does obstruct something, it just obstructs the space. Okay, and then what we want to do is we want to see the start and then the end. So let's see what happens with that. Oh, and then I actually need to put the values in there, start and end.
Would this one become a printf?
Oh yeah, you're right. This should be a printf because we have a print directive this time. Whoops. See, my Vim is like horrible. It's like kindergarten Vim. Okay, let's see here. So let's run that test again. So we got a forever loop here. So that's a problem. We're not exiting. Why aren't we exiting? We're always printing start 0, end 1.
I think there's a case we didn't handle where like needle is not in the haystack.
So one thing I'm going to do is I'm going to put a limit on how many times this for loop can run, just so that we can analyze the entire history of what's going on in this case. Let's say I'm going to say 10. I don't think it should take more than 10 times. And then if I run this again, so it was searching for needle 3 in haystack 1, 3. That's the one that it failed. And it originally started off with 1, 0, and then it went to 1, 1, and then it did 1, 1 again, and then it did start 0, 1. Oh, also, we might be looking at multiple different cases here because we're not using a subtest for every single search. So another thing I'm going to do is I'm going to put in subtests. We talked about this last week. There was a lot of desire from people to have subtests so that we could figure out where is stuff failing, because it's hard to look through the logs to find things. So I'm going to open up the test file. And what I'm going to do is when we run this, I'm going to run a subtest for each one of the haystacks that we have here. So, Ali, can you say again what you thought the problem was with the current solution?
I thought it was we can't find the needle in the haystack, but that's wrong because the test that's failing, in the test that's failing, the needle is in the haystack.
Okay. Yeah, I think in all these test cases, except for the one that returns -1, we always have the needle in the haystack. And this one actually succeeds because it's the case that it's empty. And in the empty case, it just automatically returns -1.
Yeah, we might want to add a case where needle is not in the haystack.
Yeah, good idea. So we can do that right now while we're modifying this test. So the subtest is going to have a combination of the name, the slice, and then the needle that we're looking for. So I'll say dash %d. Okay, so we have s dot haystack and s dot needle. So all I'm doing here is just adding another layer to the test. So originally we just had the name of the test, and now we're going to have the name of the test divided by the haystack and then dash or hyphen the needle. I don't know how that's going to actually print, but we'll see down here. This is how it prints. It has the haystack and then dash and then the needle. And what we'll do just to clean it up a bit is we will get rid of the space here. These spaces are just creating underscores, so they're not really needed. There we go. That's a little cleaner. Okay, cool. So now we can see we passed the first three tests, and then we failed when we tried to find this case. So in this case, so this is kind of interesting because the first case we had two elements in the list and we're looking for the first element. In this case, we had the same list of items, but we're looking for the second element. So the function, the solution is failing for when we need to go right. That's my first guess, is that going right is flawed here. So I think what we need to do is also print out what mid is when we're doing this. So I'm going to do I'm going to print it out right here. Just so we understand what we're setting in these different operations here. So we see start equals mid when we're going right. And then another thing is I want to know when we're actually doing these operations, because it's not obvious here if we went right or left. Or maybe it is obvious. Let's try that again. So the problem with using the logs is that they don't print with the it doesn't print along with the test case that we're doing. So I'm going to focus the test so that it only does the one that we're concerned about. So the one that we're concerned about is this test right here. That one succeeds. Which one was the one that failed? It was -3. Oh, no test to run. So this syntax, it probably doesn't work in the shell, I'm guessing. I'm going to try to quote it. It might be something that my shell is actually interpolating. Okay, that's not cool. So to aid with a logging, what I'm going to do is I'm just going to put I'll put another emoji. Let's put in, oh, we got the sunshine here. Let's put the sunshine in there. And that way we know when it's the test case. And I'll also do haystack needle. Okay. Let's try running this again. So if we look at our logs here, so we have now we can actually see the logs a bit better. Oh, maybe I missed something, but oh, we were looking at the test summary earlier, so that was my bad. The test summary doesn't have the logging, but we can still see that the individual cases passed or failed over here. Oh no, it doesn't tell us that it passes or fails when we're looking at the logs, so we still have to go look down below for that. This is the case that failed. We had 1, 3 in the set, the haystack, and then we were looking for needle 3, and it just got stuck. It was looking for start 1, end 1, and mid 0, and then it was it looks like it went right. And when it went right, so this is what I think the problem is. On line 37 here, we assign mid to start, but the problem is we're dividing the difference of start and end, and we're ending up with end is 1, start is 0, right? Because it's a 2-element list. 1 divided by 2 ends up being 0 when you have an integer and you don't have a it's gonna truncate downwards, right? It's gonna round down with an integer when you divide 1 by 2. So that's the problem, is that we're losing precision here. So what we could do is we could try a hacky thing, and we could just put +1, see what happens there. That might fail on some test cases, though. Let's see what happens. So now that test case, it still does not succeed. Searching for needle 3 in haystack, got index 1 but wanted 1. Got index 1 but wanted 1. So it's getting index 1 because
it's getting index -1.
-1. So that's not what we want either. So I think the problem is that I think it has to do with this end minus start right here, because what we're doing is we're subtracting the beginning from the end, and sometimes we end up with 0, which is not really what we want, or maybe that is what we want. We also have this problem here, end equals mid. It's very similar to this. So I feel like we're going to run into problems in other test cases as well. So if we look at the failures here, we're getting some other problems in places where we go left. So yeah, I think we should try to modify this. So when we want to go to the left, I'm going to exclude the mid, because I think that once we've determined that the mid is not what we're looking for, we can get rid of it. So I'm going to try this. And then I'm going to try this. Let's see what that does. And dealing with these indexes is not fun. This is like the annoying part.
Yeah, it's like some off by 1 error.
Yeah, the most annoying problems. So that still doesn't fix it. We're stuck in a loop here, 1, 1, 0. So instead of doing that, I'm going to let's see here. I'm going to look at this. We've got end minus start divided by 2. I'm going to put a +1 in here and see what happens. Because I think part of the problem is that we shouldn't end up with 0 there. So now this passes, but then the next one fails. Searching for needle 5 in haystack 135, got index -1. We're ending up with these negative values, and I believe what's happening is that we're ending up with an end minus start that results in a negative value. So if end, let's go look at what's happening in that failing case. So that failing case is 135 needle 5. So if we go to 135 needle 5.
I think in this case, it's just running out of iterations, because like we limited the for loop to 10 iterations. So it just gets stuck, and then it runs out of its 10 iterations and then returns -1.
So in this case, there's only 3 elements in the list. So it should take at most 2 iterations to find the solution. because what it's going to do is it's going to check value 3, right? And then if 3 is less or if 3 is not the value you're looking for, you go right. Whoops, what happened there? So when we see start 1, 2, mid 1, here's the problem. So start is 1 and mid is 1. If you go right and you assign start to mid, nothing changes. It's the same value again. That's the problem. So if mid were 1 higher, that changes things. It reduces the scope, right?
Yeah.
So let's see what happens there. Now it succeeds. You see that? Or actually, that's meta. Sorry, that's the wrong one. So this one fails now, and this one fails. So this is fun. So if we look at the data here, 1, 3. So we start off with start is 1 and end is 1. Start and end are the same value because of this. Why are they the same value? Start is 1, end is 1. Oh, this is why. Because it's the length of haystack. Oh, this is an error on my part. I put the value at 0. That's why. You see this?
Oh, yeah.
Yeah, this is why. That was a goof. I was going crazy trying to figure out why this wasn't working. That's what happens in a live coding exercise. Everything that can go wrong will go wrong. You make the dumbest mistakes possible. Okay, so that's why we run into problems. So I think a lot of the stuff we added in here, we can get rid of. All this hacky stuff that I thought would fix the problem, but it probably wasn't. Let's see what happens here now. And just for consistency, I'm going to go back to what we had before, which is just end equals mid, start equals mid. Let's see what happens now. So we get passes everywhere, except we don't get passes on 1, 3, 3, once again. So if we go to what's happening in 1, 3, 3, start is 0, end is 1, mid is 0. Second iteration, same thing, same thing, same thing. And that's because mid is 0. So I'm going to put back in the +1. So we get a different value. Or what I can do is I can put the +1 -1 into here, like this, and like this, and see what happens. So now it still doesn't succeed. You got any suggestions, Ali? Start equals mid +1, 1, 1. And then
Yeah, so it looks like it shrunk the area of the list it was looking in, because you can see that start is 1 and end is 1. So you're now looking at basically one element, but then like the success case is needle equals haystack at mid, and mid is always 0 for some reason. So we basically have to fix that mid should be 1 if start is 1 and end is 1.
Yeah, so I think the big thing is we have this round off issue, right? Where, well, we have round off issue, and then we have the issue where you have one where the start and end are the same thing. So I think one way we could fix this is what we can do is always make the mid the start, whoops, start plus half of start plus end. Does that make sense? Or sorry, end minus start divided by 2. So that way, when start is 0, or when start is 1, this is going to be 1, right? And then when end minus start, which is going to be 0, is divided by 2, that's going to be 0. Then it'll still be 1 for mid, if that makes sense. So let's see what happens here. Now it passes. Yeah, so that was the issue, is that it worked on the first iteration, but it didn't work on the second iteration, because if we were going in, if we went right, because the in the first iteration, 0 is a valid number because the left of the list contains the index 0. But when you go right, 0 is no longer a valid value. So we have to do something to make sure that this doesn't turn to 0. I don't know if I'm explaining it well. Does that make sense?
Yeah, that makes sense.
So if we put start here, which is guaranteed to be a positive value when we're going, or it's always going to be a non-zero number when we're going right, then that keeps us within the range. We have to keep that midpoint within the range. So yeah, that was that was the little bugger. So now we have a solution that is iterative, but how would we do this recursively? And how would we do it recursively in only a few minutes? Any thoughts?
I haven't actually looked at recursion in Go. Does Go have tail recursion, like tail call optimization?
I don't know how it's done, actually. I don't know. I'll have to look that up. Let's put a follow up here. So we'll look that up when we get back to it. So just to wrap things up, the what we have to do is we have to basically provide all of these parameters, the start and end, but instead of going into a for loop, we're going to be making calls to a secondary function, or the same function over and over again. I don't know. Can it be the same one? No, it'd have to be a new function signature. But yeah, I think that's all we have time for to do this. We'll probably have to do this next week. This keeps getting delayed. I really want to do the recursive one. I think that should be really fast now that we have the iterative solution, because we're just going to use the iterative solution to get the recursive one. We're just going to rewrite it a bit. But yeah, I think that's it for today. Do you have any comments, Ali?
It's pretty good. Yeah.
Okay. This is technically supposed to be an easy like algorithm to do, but all of these little index things, they just like take a ton of time, right? You're like, why isn't this index correct? Why isn't this division? You
Yeah.
have to remember, oh, if you divide this, it's going to truncate the value, or um, you know, if you move it to this side, then this index. It's like all this like index math that you have to do to keep everything organized. But get better at it with practice. So I think this is good exercise. Did I?
Yeah.
Okay, there we go. So I'm gonna upload these solutions, and I'll upload this video. And next week we will finish binary search, and I will be trying to figure out a good problem from this concurrency in Go book, and we'll do something that uses channels and sync primitives, and we'll try to simulate some work. Maybe we'll try to mix in a computer science fundamental algorithm that we can do as like a distributed work kind of problem. But yeah,
I have an interesting one for that.
sure.
It's quite challenging to come up with the solution intuitively, I found, but there's this concurrency problem called the dining philosopher's problem, which is basically like there's like 7 people sitting at a table, and then there's like 1 fork to the right of every person, but there's like only 6 forks. So you have to like figure out how to synchronize like who picks up the fork and when to eat and stuff.
Yeah, we can definitely do that. I just saw an implementation of that on Leak Code. So I know there's some test-driven ways to play with that. So I'm going to take a look at that, and maybe that'll be a good introductory problem to get into concurrency, and then we can figure out something a little more complicated down the road.
I'm quite
So,
interested to see how we can like test the concurrency because I have no idea how we would do that.
So the big thing is we need to come up with the success criteria, and then we need to use the Go race detector. So the Go race
Okay.
detector. Well, another thing is if we end up with a deadlock, because I think what the dining philosopher's problem does is it introduces like deadlocks, right, where like they can't
Yeah.
proceed with work.
Yep.
So if we end up with a deadlock, the Go runtime will. I think the Go runtime will just kind of crash if there's a deadlock. It'll detect that and it'll
Oh,
just
okay.
yeah, if we have that, actually, let's do a little example here. Let's see here. Or actually, I'll just do it in this file. So
I
if
feel
we
like
have,
that's a pretty unique thing, like for a language to detect deadlocks.
yeah, it's a really cool feature. And if you run the race detector, then it can tell you if you have like a read and a write to the same value without using a lock. It knows that you're doing something you're not supposed to. But the problem with the race detector is that sometimes it doesn't detect the race if the conditions during runtime aren't present. Like you might only detect a race time some of the time, depending on how you wrote your code. So that can be an issue. But if I have this is a really easy way to do it. If I make a channel and then I just try to read from that channel, this should deadlock because there's no one writing to this channel. Channels are supposed to be between two different they're supposed to be between two different Go routines. This is only one Go routine here. It's just the Go routine that I'm writing in right now, the test deadlock Go routine. So if I try to run this, what did I do wrong? Oh, I'd put Go run. I don't want Go run. I want Go test. So here, it's done. Okay, so it didn't tell us the deadlock then, but then if I add the race detector, doesn't do it there either. Interesting. Yeah, I'm not sure why it lets me do that. Maybe, I'll have to look in this a bit more because it will tell you when you have like all your threads asleep. When you have the race detector on, it'll definitely tell you. And I believe if you have without the race detector, if you just like compile an executable in the Go runtime, if all of your threads are asleep, I think it tells you that. So we'll have to take a look at that a bit more. I'll put a note here. What happens in Go when you have a deadlock? And then we both want to know during tests with the race detector and at runtime in an executable. And yeah, have a deadlock. All Go routines are asleep or blocked. So yeah, I'll follow up on that. And yeah, I think that dining philosopher's problem, that's probably a good way just to introduce syncing and locking between competing Go routines. We can start with that. And then we'll just move forward. I think this book might have it in here. Let's see here. I don't see it in the index. Yeah, we'll start with that. That's a good simple problem. Got anything else?
Nothing comes to my mind at this time. There's definitely some cool stuff in the area of concurrency.
Yeah, there is, especially with Go, with the Go routines. There's a lot of fun things that you can do with it, and a lot of cool sync primitives in Go. We can definitely explore those individually and see, how to use them. Cool. Well, I'm going to call it here. We're a bit over. Thanks, Ali, for joining. Next week we will definitely wrap up binary search, and then we'll start the Dining Philosopher's problem. All right. Have a good weekend.
Thanks, Paul. See ya.
Bye.